Hi and welcome back. Today's episode is about linear models comparison. We will use different libraries to compare our model's performance, checking models assumptions, comprehensive visualization of model diagnostics and how to read them, and how to use this model's performance to select the best model. Let's use Easystats to help us in this task. Let's go now. Let's start creating some models now. Let's first plot the libraries Easystats, and this one is including the library performance that we're going to use certain functions. You will see that here we already have performance, so you don't have to load it 2 times. As you can see, we have here different columns, different features of a car. Like as you can see, MPG, cylinder, displacement, horsepower, weight of the car, speed for running a quarter of mile, and so on. Then we're going to create this linear regression model. First, as you can see, we're going to select MPG as our response variable. We're going to select two different features or independent variables. In this case, is weight and factors. You can see here where we have different cylinders, 6, 4, 8. Okay, that's what I'm using factor. This is a categorical variable. And there we go. We just saying that this information is coming from empty cars, and we'll create our first model. Let's see. This is our summary. As you can see, all these variables I chose are significant because I can see it here in this column, PR. Okay, and as you can see, factor, cylinder with 6 and 8 respectively. That means that cylinders with 4 is our base. Remember, is our reference. We have all these variables that are significant. Other things to consider is the R-square. This is our R-square. This is a measure, performance of our model. Now, we will create different other models. Model 2, for example. In this case, I change, I say weight, okay, and horsepower. See model and summary 2. These variables are significant too. Weight is significant as well as horsepower. And check the R-square. Okay, a little bit lower the other one. You can create a model adding horsepower to model 1, for example, and you can compare. But let's see. I'm going to create a third variable where I'm not going to add cylinder, but I'm going to add VS. VS if it's V shape or not in our instance. Okay, if it's V shape, 0 for no. You can see it here. There you go. And if you have same problem with that, just come here to help. And then you type empty car, and you will check here. V shape, 0, and 1 straight. Okay, VS. That's the reason it's called like that name. V shape is 0, 1 is straight, and we create our third model. There you go. As you can see here, we have a multiple R squared, our R squared, even greater than the other ones. That is not only one metric that we compare another matrix. Remember, when we are doing this, we can compare the mean square error. Okay, let's see model performance. You can use this function R2 that is coming from performance. You can see it is giving us the difference R squared in our model, but remember that this is for training. Okay, training. Okay, if you want to do more steps, you can select some training set and then testing set and check that performance. Okay? You can use the different functions. Well, collinearity. Remember that when we are creating models, maybe two variables are explaining the same thing. And with collinearity, R will provide us our PIF. PIF is variance inflation factor. Influence factor, as you can see, if this value here is lower than 5, we're okay. Check even that confidence interval. is lower than 5. Okay, so run this if you are considering that you can have two variables explaining or more very correlated among these variables. Okay, now not only this, but we can create for the model 3. Okay, model 3, there we go. In this case, because I was adding an interaction, look at here, maybe inflated, of course, because we have these two terms that are interacting. Okay, so it could be misleading us. Then model 2, there you go. These two variables don't have any multicollinearity. All right, as I was mentioned before, performance. This function allows us to check MSE. Okay, for it 3.2, then we extract from model 3 this value. Okay, you can see, and of course you can compare from model 1 and so on. Okay, we can be doing this as well as this other function MSE that is gonna give us, let's see, model 1, same value. Okay, performance or MSE as well. This is a different way to do it. However, look at this model performance. This is even better. This one is going to provide us different metrics of our model's performance, not only by one like this. Okay, R2 or MSE, for example. Let's check here. We have the IKK information criteria as well as the Bayesian criteria and R square and the root mean square error and the sigma as well. Okay, this is super important. Huh? It's given a different metric at the same time, and you can run for the other models, and then you can compare. Based on what? You can choose if you want to decide based in R squared. Well, that model number 3 is winning, you can say. And IKK information criteria, you can say that model 3 is winning too, because the AIC has to be the lower possible, near 0. Okay? And you see the errors, they have minimum value here in the model 3. So using model 3, this is how we can compare different models. But don't forget that we have to check model assumption. This is something that some people just skip when they are using linear model. Is they have to check, remember how we call them? We call them line, because we are investigating linearity. We are checking to independence, the errors, or the different observations, normality, and as well as equal variance of the errors. All of this, we're gonna check them now. Okay, and of course, as you see, there are other assumptions, is multicollinearity, and we can say some outliers and so on, but these are the ones that we always check. Now let's see. In the past, we had check the function check multicollinearity. In this case, Homoscedasticity means the opposite of homoscedasticity, of equal variance in this case, and let's check. It's telling me here heterogeneity, non-constant error variance detected. Look at the p-value. We have a p-value lower than 0.05. That means that our model number 1 is presenting or is shielding heteroscedasticity. Okay, it's not good for us. Let's see model number 2. Yes, error variance appears to be homoscedasticity. Even if, remember that we were using weight in this model and in this model, but I changed the variables, category of whatever cylinders, and here I'm using horsepower. Look at the model 2 is improving, as you can see here. It's improving. No, it's not improving actually. Here, only the BIC is improving. The R square is a little bit lower than model 1, but is following the model's assumption. That's good for model 2. Let's see now model 3. Let's see, let model 3. Okay, there you go. Model 3 is the best in all aspects. Not only has better R-squared and other criteria, but it appears to be homoscedastic. Okay, the errors variance appears to be homoscedastic. Okay, we have equal variance. That's important. And we can check other visualizations to understand if we have linearity, independence, or normality. Let's see how. First known method is to just run plot model 1, in this case, for example. And look and see here, the console, and you will have different plots here to your right. Residuals versus fitted values. It is used for homoscedasticity. In this case, we should have some pattern like this, but as you can see, there is some problem in this area here. That's why it was rejecting homoscedasticity. Okay, let's see another thing. For example, normality. We're having a little bit of problems in this way too. Okay, and we can see as well as case location with the standard residuals and some other residual versus leverage and cook distance to see some influential points. And as you can see, there are some observations that are presenting us some problems around here, right? Okay, that's one. But other way that I'm going to introduce now using a library, Easystats, is where we can just use the function check model. In my case, I have to run this. I'm going to run model 3. It's going to be better. And we're going to save it. Format, we're going to save our output in this format and model 3. And it's creating, as you can see. And just turn off. There you go. How to see it? Well, you have to go to your working directory. In this case, I have to go here and open this plot. And I have here my plot. You can see we have some interesting and very colorful plots. You can see here that we have our density of MPG. You can see, okay, MPG looks normal. That's not a problem in this case, but the linearity, you check here, fitted values and residuals. It's look like we have some scattered points around it. That's okay. It means that we are following some equal variance. It is not having some deep hole around here, like the model number 1. And with the standard residuals, look, it's around -1 and 1. And we have good output, in this case, influential observations that are low, less than before. Check collinearity. We don't have any problem. If we don't compare when we are having this interaction, and look at the normality. Maybe it's some certain points here, but it's not a big deal because we have homoscedasticity. That is the one that concerns us the most. Now, let's see how we can compare all our models in once. Plot compare performance. This is gonna let us to compare different models. If you wanna could plot how to compare our models, look at that names there. And we here rank equal true. Important. What does it mean? Well, it means that this radar plot will give us the best model. In this case, you can see the rank. This is rank, okay? Check model number 3. Is the best in R squares adjusted, root mean square error, sigma, BIC, all of them, okay? Not only is saying that this one is the lowest, as you can see, but this one is saying that R squared is the highest, okay? That is because it's rank. And here we can say that model 3 is the best. So if we want to predict miles per gallon, we should use a model with some interaction between horsepower with VS, a V shape, or not, in our car. This is how we use the library Easystats in R.